and then you can use it to somehow approximate any periodic function as a sum of sine, cosine, or exponential terms. Now we want to talk about something new, which is Fourier transformation. Fourier transformation, again, is a transformation which will help you to transfer your system or signal from time to frequency. So it does very similar thing as Laplace. However, the application of it is in the signal handling. So if you want to do the signal analysis, Laplace cannot be useful. Again, you can use it to transfer a system from time to frequency, but you cannot use it for anything else, so it's not useful. But if you want to do the signal analysis, voice analysis, music work, and something in this domain, then we always work with the Fourier transformation. Like Laplace, we have the Fourier transformation formula and inverse Fourier transformation formula, as you can see them on the screen. The notation we use is, instead of this italic L we had for Laplace, is F, you can see there. And when you take the Fourier, it will become small f, will become capital F. So this part is the same as Laplace. But instead of S, we have omega. So we have capital F of omega, which is the integration of minus infinity to infinity of f of t e to the power of minus I omega t dt. And this is the formula for inverse, and you can see the notation here. If you want to do the inverse by using the definition, this is the one you have to use. Yes?
Is omega also a complex variable, or is it?
Can be, yeah. This Fourier transformation has a linearity property. So what does it mean? It means that if you do A and B are some constant numbers. So if you do the linear combination of two signals together, and then you take the Fourier transformation of it, it's the same as if you take the Fourier transformation of each signal first individually, and then multiply it by your constant number, and then add them together. So this is one of the useful. It has a lot of properties, and this is one of the useful ones.
I didn't understand what you just said about linearity property.
It means that no matter how you add or subtract two signals together in time domain, you see exactly the same summation or subtraction of these two signals in the frequency domain as well. We had this in the Laplace, so it's very similar to before, but now instead of L, we have capital F, and this F. Good, thank you. I think from now on I should have a translator in the class. Yeah, okay.
That's just some English words.
Yeah, I know, I understand. That's fine. And thank you that the other ones help you.
Yeah.
Now let's look at the formula we had for the Laplace. Let's assume I want to take the Laplace transformation of f of t, and we know that it will become capital F, and because I don't want to mix it with this new one, I write the Laplace here. So f of Laplace in S would be the integral of 0 to infinity of f of t e to the power of minus st dt. This is the formula of Laplace. You have seen it before. And as you know, we can take the Laplace only for causal signals because we have only integration in a positive part. Can you remember it? That was one of the prerequisites of doing Laplace. Always the function should be causal. Now, let's look at the formula we had for this one. Which, if we do the Fourier, it will become capital F of omega, which is integration to two parts, negative and positive part. So it will become minus infinity to 0 of f of t in reality, we only works with the causal signals, so we don't have negative, the signals in a negative domain or a system which operates in a negative time domain. So now let's assume that, because we talk about the reality, this part is 0. So now let's compare the formula I have here, because at the end this will become only positive range. Now let's compare this one with the Laplace. What's the difference between them? Yes, please?
Omega instead of S.
Exactly. So the only difference we see is that instead of minus st, we have minus omega t. So we can say that when we work with the causal signals, there is a connection between Laplace and Fourier transformation, which says that if you have the Laplace of the function, and instead of s, you replace it with I omega, and sometimes in some books you can see they write it as omega without I, but they are the same, then you have the Fourier transformation of the signal. Or vice versa. If you have this one, you can replace it with s, then you have the Laplace of it. So as far as you have a signal which is causal, it operates in positive time domain, then always and always we have this connection between Laplace and Fourier transformation. Yes, please.
Why was it that minus infinity gets removed while infinity gets
Because in reality, in real application, all the signals are in a positive time. You don't have a signal in negative.
Okay.
That's why I said that, okay, because let's assume we work with the real world, not mathematic world for now. So this part becomes 0, and the only part remains is here. And as I told you before, the Laplace is also for only causal. So if it's only causal, this is valid, and this part for Fourier transformation becomes 0, then this is the connection between them, always and always.
Yes.
Why did the from minus infinity to 0 become 0?
Okay. What is the causal signal? The causal signal is a signal which only has values in positive, like this one. Another example is u of t, if one is here, for instance. So these are an example of causal signals, and they're, in a negative domain, they are 0. So if we consider only causal signals, so in a negative part they are 0, the multiplication of 0 by exponential is 0, that's why this part becomes completely 0. So there is no area under these two lines here. This is the definition of integration.
Yes, but in Fourier, it doesn't have to be a causal signal.
No, no.
So it's only for the case that you have a causal signal.
If you have a case which is not causal, this is this pink one, like this. Then in this case, of course, this will not become 0, and this equality is not valid there anymore. So this is only and only true for causal ones. But yes, if it's not causal, this is not 0. Yeah. Let's look at an example. We have a causal signal f of t, and now we want to find capital F of omega. Here I want to show you how you can use this equality connection between Laplace and Fourier transformation. So as you can see, f is causal. Why? Because it's the multiplication with u, so automatically this part of the signal becomes 0 because of the multiplication with u.
Why?
Because u is this blue line. When you multiply any signal with this blue, it will make the negative part 0 automatically. That's why this f of t is always causal, because it's the multiplication with u, with this blue line. Okay? So now you know this is causal, and if you use the Laplace tables, you can use I think it's table 7.1 7.1. And then you find that f of Laplace will be 1 over s plus 1. And then now if instead of s you put I omega, automatically you have the Fourier transformation of it. And again, we have tables for Fourier transformation as well. Let me show you. Just a second. Table in tables.
Laplace is 7.2.
Is it 7 point? We have 7.1 and 7.2, and this one I think is in a 7.1. Row number 4 or 5.
It's because it's 7.2 and 7.3.
Oh.
The table.
Then sorry.
Yeah, but yeah. No, it's not a thing. I just want
Is
to
it?
put that.
Okay.
Okay, 7.2 is the one with the 5 at once.
Let me load. Okay. We have other tables which are in Learn already as well, which are table 5.1 and 5.2. These are Fourier transformation tables. You can also use these tables for finding the Fourier transformation, and they are as useful as Laplace tables. So just download them and use them for later on. Any question for this example? Yes, please.
And you always use the Laplace table and just change the S with the...
As far as it's causal, yes.
Okay.
However, if you go to the Fourier transformation tables, you have a formula like this one there as well, so you can directly use that table as well. So I need to erase the boards because I need it for the second example. I'll do this one. Let's look at the second example. We have the rectangular pulse signal with capital T, which is a positive number, and it's defined as this one. I will plot it first, and then I will explain it more. Just give me a second. So, okay. This is called rectangular pulse signal. And the notation we use for writing it is rectangular small t divided by capital T. Something which you need to keep in mind is that this capital T here is not the period anymore, because we don't talk about the periodic signal anymore. The capital T here is the width, I think it's called, from here to here of the signal. Yes, please.
What did you say, capital T?
Width.
Width. Okay, yeah, width.
Okay. So it's not the period anymore, and it's defined from here to here. And the height of the signal is always 1 based on the definition of the rect of small t divided by capital T. And it's also written here. It's equals to 1 for the range of minus capital T over 2 to plus capital T over 2 and 0 elsewhere. Now we want to find, this is our function f of t. And now we want to find f of omega, the Fourier transformation. You can find the formula for such a signal in Fourier transformation table and directly use it that one. But here I need to show the proof to you first. That's why I do that. But in exercises or exams, you don't need to do the proofs. If it is in a table, just use the table. So I use the function of the Fourier transformation, which is minus infinity to infinity of f of t e to the power of minus I omega t dt. The formula says that it should go from minus infinity to plus infinity. However, our function f of t, so I can replace this with rectangular of t or capital T. This goes only from minus capital T half to plus capital T half. So I can change the integration then for this range the function is 1. So 1 times e to the power of minus I omega t dt. And multiplication in between. Any questions so far? Yes, please.
The rate, what does that stand for?
What is rate?
The RECT of.
It is the short term for rectangle.
Okay.
In English,
Yeah.
it's called rectangle, and that's RECT. I mean, if you want to write the whole word, it's a start with RECT.
Yeah, but it's a function, a rectangle
Yeah.
function. Okay.
And you can see the shape is also in the
Oh, yeah.
rectangle shape. Yes?
Why did it become 1?
Because, as it is stated there, it has the value of 1 always for this range.
Okay. Yeah.
And that's why the 1 comes
Yeah.
here. Was it the same question?
Yes.
Okay.
Wait, what? Is it up there?
It is written there. It's, yeah, you can see it says that this function is equals to 1 for the range of minus capital T divided by 2 till plus capital T to 2. So it is written there. And you can also see in the plot that the height here is 1. Yes.
Is there a reason you didn't use the tables from?
You can do that, but because I'm the teacher, I have to show you the proofs.
Ah,
This is my task. I know that the students don't like the proofs, but I have to do that anyway. And you know, I already skipped a lot of proofs, so I cannot do it anymore.
it's just confusing because you have an option, but you need to prove it. So sometimes.
I do that. You as a student don't need to do proof,
Okay.
but I have to.
It's.
Yes, but it is to give us an understanding
Yeah, of course,
how
yeah.
the tables
Yeah.
was produced.
How they did
Yeah.
it, yeah. And if you want to do it later on for something else, you know how you should do that, yeah. Yeah. Now I need to do this integration. I consider two scenarios now. One when omega is 0 and one omega is not 0. Why I do that? Because if omega is 0, it's very easy. So I can do it right away. The other one is not very difficult, but it's a little bit difficult than when omega is 0. We don't have this integration by part anymore, so I think that's good. Okay. So for omega is 0. So f of omega would be the integral of minus t 1 times omega is 0 and e to the power of 0 is also 1 dt. And if you do the integration, it will become small t from minus t over 2 plus t over 2 So at the end, the result for omega 0 would be capital T. Now, if omega is not 0, it will become f of omega becomes equals to minus t half plus t half of 1 times e to the power of minus integration in Laplace lectures a lot. So if we do that or use this, it will become 1 over minus I omega e to the power of minus omega t from lower limit to upper limit. First, we put the upper limit, 1 over minus I omega e to the power of minus I omega minus 1 over minus I omega e to the power of, this minus times minus make it a plus I omega. Yes.
It just looks like in the brackets. It looks like it's minus t in the top as a top limit. Yeah.
Here,
Yeah. It should just be t, right?
no, the range is minus capital T half to plus capital T half.
Yeah, but it just looked like it said minus t in the top.
Oh, okay.
I don't know if it was an old.
Maybe.
Or-
Let it.
but
Is it now good?
yes.
Yeah.
Now I have
Perfect.
it.
Okay. Now what I do, I make the factorization of 1 over I omega, only the plus, not the minus. So it will become, and you know, minus times minus make this plus. So it will become e to the power of I omega capital T over 2. I have a minus here, minus e to the power of and it is one of the Euler formulas. I think we can change it to one of the Euler ones.
Sign.
Yeah, I need to multiply by 2 and divide it by 2 at first.
Okay.
If we do that, it will become equals to 2 over omega 1 over 2I e to the power of I omega 2 minus e to the power of yes.
What did you do after the
Multiplying?
Yes, I don't quite understand.
What I did, I said that I multiplied this 2 by 1 over omega only. So it is 2 over omega. And then I have another 1 over 2 which I multiplied by I term because I want to show you that how this becomes sine. So actually this term is the same as 2 over 2I omega. I just did it in this way such that it becomes easier for you to see why it is now sine. So they are the same, just different way of representing to make it much more clear.
Jeg er med på, at man kan ikke se.
Which part is not clear?
I don't quite understand why you. I understand you need to have over 2 to get into Eulers, but it's not clear for me.
You know, let's multiply this 2 by the top here. So it will become 2.
Yeah.
And then you multiply the 2 at the bottom with the denominator here.
Yeah.
So it is 2 divided by 2I omega.
Yes.
So either you can write it in this way or write it this way. Both are the same because the multiplication is in between.
And what do you do further on?
I did that. I said that I have 2 over omega, so I keep it as it is. But this part divided by 2I is the Euler sine formula.
Yeah.
Okay, you can also bring this here.
Yes, yes. Now, there it is. There it is.
Good.
Okay. So.
So maybe I should back to the original. Okay. Now, this is 4, 5, and 5, 6. So now we found that f of omega is equals to capital T if omega is 0, and it is 2 over omega sine of omega T over 2 for omega not equals to 0. So what I do now, I will factorize capital T from both terms and bring it out. So T, it will become 1 here, and for omega 0. And this one will become 2, no, yeah, maybe write it first in this way. Omega T sine of omega T2 for omega not 0. So you can see, if you multiply this T by 1, you get exactly the same expression as here. And if you multiply this capital T by this one, this T and T cancel out. So we get what we have in the middle. I have a reason which I did this, and I will show you now why. This can be also written as a T times 1 for omega 0. So I will bring this 2 from numerator to denominator. So it will become 1 over omega T2 sine of omega T2. And this structure is a sinc function, the one I showed you a couple of weeks ago. So it will become T times sinc of omega capital T2. And this is something you have in a table for rectangular. And if you don't remember sinc, this is the structure of sinc. It says it's always 1 for x equals to 0, and sine of x divided by x, so these two should be the same, for x not equals to 0. And that's why I did all these rewriting in a way that what I have in the parentheses becomes exactly the same as what I have. I mean, what I have here becomes exactly the same as what I have in the parentheses. Then it's sinc function. Yes?
It's not clear or why did you do that?
Because first I want to prove how you can reach to the formula which is in a table of Fourier transformation.
Yes.
And another thing, I did all this rewriting to show you that this structure is a sinc function. What is sinc? Is this one. So it should have 1 here always. So I have 1. I'm good to go. I have it also here. I'm good to go. But if you look at this, the way it is written here, you cannot see that it should be sine of something divided by exactly the same, sine of x divided by x. So that's why I did all this rewriting in a way that you can see the similarity. Yes, please.
Just to be sure, I'm assuming that t over 2, you implemented that to get rid of the 2 as the numerator?
Actually, I moved it from the, let's do this. 1 divided by 1 over omega capital T divided by 2. Are you agreed that this is the same as what I have here? Instead of 1, I wrote 1 divided by 1.
Yes.
And this one, I multiplied omega by capital T divided by 2. So this is exactly the same as what I have here. did the reverse of this, and I moved there. So I had this one, so I did the reverse to get this one.
And you said you did this so it matches the
It
equation
matches to the
table?
formula of this in a table 5.2 or something in there.
Alright.
So always and always, the rectangular signal, the Fourier transformation is this table, this box, which is the same as what you see in the tables. Yes, please.
Just make sure that the omega on the second one is not 0, right?
Yeah. Thank you. Thank you. As you can also see on the slide, it shouldn't be. The second one is for omega not 0.
Yeah.
Yes.
You just put I've never heard of the term safe before. I don't know if I should have.
We talked about it a few weeks ago, and I showed it there, and I mean on the board. The sync function. Let me show the shape. Maybe then it will become much more clear. Just give me a second. I don't know if you remember it, but I showed this a few weeks ago, and you can see always the sync function is sine of something, which in this case is pi x, divided by exactly the same term as you have in the parenthesis. So whatever you have there, you should have division there as well. I mean, it should be the same. If you have it, then it's called a sync, and here you can see how it would look like. I mean, two examples for it. Yes.
Do we have to do this transfer at the exam?
I mean, these computations?
Yeah.
No, you just
No,
go
just,
and use tables.
Just to look at that 1 over omega t.
Yeah, then just the
To
only
make
thing,
that
you should
sync.
identify what is capital T. I have an example in a second. And then when you have capital T, put it there, put it here, and then write the formula for it. We have an example in a few seconds. Then you can see how we can use the formulas. Let's look at this example. I give you some time, you try yourself first, as usual, and then we solve it together. Because I want that you try as well. So here, it says that we have the signal, which is the shape as what you can see. First, express the signal f of t as a rectangular power signal. So what I mean here is that rewrite the function as a rectangular pulse signal. Maybe a summation of two rectangular or subtraction of two rectangular. So first you need to do this, and then after that we want to find the Fourier transformation. You don't need to use the formula. We want to use you don't need to do the proof. We want to use the formula. So first 5 minutes, so you can think about it, and then I will solve it here on board.
Good.
It is the combination of two rectangles. Just think about it for 5 minutes, and then I will explain more after that.
Altså den er 1 og minus 2, altså plus 2, plus 2 som er 2 og minus 1.
And please take a picture of board number 4 if you have not done it, because I need it. Board. Yes,
Nå, ja. Det er også torsdag, fredag, der er det kakao. Jeg er ikke så god til morgenmad, så det starter lige min dag, så det kan et eller andet. Når man skal tidligere op. Næste semester har vi kun lektioner om morgenen. Så, og i Lyngby.
Ja, sådan som Lyngby har.
15 Lyngby, 10 herude. Men det var kun godt for mig.
Det var godt for dig.
Ja,
Jeg tror, det er for meget på Lyngby faktisk.
Henrik tror jeg faktisk det samme. For ham. Jeg forstår ikke, hvorfor det er så fucking svært at komme til baller. Altså, tager 100 år.
Ja, men det gør det virkelig. Men det er også, altså, jeg ved ikke, min svigermor, han bor jo også i Ballerup.
Mm.
Der er ikke på nogen...
Det er jo mig, Britt.
Ja. Der er ikke på nogen måde komme ud til, altså.
Nej, det er der ikke.
Jeg
skal have en bil.
Noget, at så tager vi den til den husstopsted, og så henter vi os. Altså.
Ja, okay. Bor hun ude på landet?
Nej, de bor i... De bor i så sindssygt langt væk herfra.
Ja, okay. Jeg har sagt 4 semester, så køber jeg en bil. Det, ja, 100. Jeg solgte jo den lige inden vi startede. Jeg kunne ikke... Jeg tænkte, jeg brugte den ikke så meget. Jeg var egentlig meget glad for, at jeg fik solgt den. Det var også 707. Det var også helt smadret. Der var ikke... Jeg har ondt af ham, der købte den.
Hvad for en bil skal du have?
Jeg kigger på det forskelligt. Jeg vil jo gerne have en brugt bil, og du kan få ret billige elbiler brugt. Men det er sådan lidt... Ja, fordi den skal jo stå udenfor, og jeg ved ikke, om det er så god en idé med en elbil. Teknologien udvikler sig altså ekstremt hele tiden. Det er måske, jeg ved det ikke. Det kan jo også være, at jeg lige skal vente et halvt år ekstra med, og det kommer an på, hvor jeg har fag. Jeg må sige det på den måde. Ja.
Og det er jo ikke en pause, du skal den til valg, og den til valg. Du skal have 3 til valg.
Hej, Lad. Nå, shit. Ja, jeg har svaret på det er meget
Så er det lige 2. Nej, til 1, ja.
Ja, hun har udvist tidligere. 27... I hvert fald der, de har lavet eksamen til. Ja, i hvert fald undervist. Han dumpede, så han skal stoppe det. Nej, i hvert fald været en eksamen.
Okay, shall we look at it together? 2 minutes, okay, so 2 more minutes.
Yes. Ja, den er jo meget. Jo, den bliver 1 gange 1 til siden, og så 3 gange 3, og så bliver det 1. Ja, så det er 1, 3, 1. Kan du så ikke lægge dem sammen? Du kan bare lægge dem sammen her og få det tid. Ja, det er rigtigt. Du skal have tidssiden. Du skal have tidssiden. Ja.
Optaget for mig lidt.
Sender 10 til 2 i den ene og 4 i den anden.
Jeg tror, vi skal finde en kvarter. Der har vi
Nej. Jo, det gør det. Men det bliver 2 til 1, 1 til 1, og 1 til 2. Nej, den er jo 1, jo, det er minus, ja.
Jeg tror lige, du er ude i at
Nej, hvorfor? Nej, fordi den burde lidt blive minus 2.
Jeg tror, du er
Hvor er du?
der er lige ting. Der
Det er godt, der er i gang med.
Ja, den er her. Ja, den
Jeg
blev
tror godt, vi skal
en.
anerkende det som en rektangulær funktion. Så det er så det her, og så to forskellige rækker,
Nå,
eller
ja.
to forskellige ting.
Yes, og det bliver plus.
Vi er nødt til at finde ud af, have nogle ting. Jo, men det har vi jo også. Den ene værdi for t, den er jo 4, og den anden værdi for t, den er 2. Det er ikke rigtigt overhovedet.
Okay, let's look at it together. So for the first part, we want to rewrite the signal as a rectangular part signal. Do you have any suggestion that how can I look at the signal such that the rectangular is there? Yes, please.
Yes, you have you have one which is 1 from -2 to +2.
So this orange one,
Yeah, so that's one rectangular function.
yes,
And then you have another function which is 2 from -1 to
exactly.
+1.
And then this purple one. So we can look at it as a summation of two rectangular signals. So let's look at the orange one for now, only and only. So I have rectangular of t, then divided by capital T. What is capital T for the orange one? Yes, please.
4.
Exactly. Again, why? Just do the comparison of the original signal here. So minus capital T over 2 is -2 for the orange one. If you do here, capital T becomes 4. So this is the first one, the orange one. We do exactly the same thing for the purple one. And of course, we should add them together. So plus for the purple one, again, I have the rectangular. Of small t divided by capital T. What is capital T here? Yes?
2.
Exactly, divided by 2. I'm not done with the purple yet. Why? If you compare this purple with the original one, you can see that instead of height of 1, I have the height of 2. So, it means that I have to multiply this rectangle by 2 as well. So, it should be 2 multiply of this one. So, I don't think that it was difficult, but of course, as you solve examples, it will become easier and easier. So now I have f of t as a summation of two rectangular ones. Yes, please.
You said it was 2 because the purple one has the height of 2.
Height of 2. Why? Because the height goes from 1 to 3. So it has the height of 2.
Oh.
But the original rectangle should have height of 1. So the height is 2 times more than this one.
Okay.
And that's why we do this. For the orange one, the height was 1, so the same as before. So it was not needed to have something here. Because it was 1, the same as before. Yes, please.
What if you are working with different functions? Can you always divide it so that
What do you mean by different function?
Yeah, if you have with the function, if it was a function, let's say the orange one, the value of the function was 300.7, and so can you divide that so you have the first rectangular function as a function with the value of 1? What if you have
It's
more?
up to you how you divide this or define your rectangle. So yes, it's possible.
But it could also, the orange one could have go to 2, and the
you
purple
could
one
see,
could go
yeah,
to
you could say that I have an
6.
orange till here, and then minus this rectangle and this rectangle. Can you see? So you can look at the problem in a different way.
Yeah.
And then of course if you have an orange like here, the height was 3 times something, then minus this one and this one together.
Yeah. I'm just thinking that there could be any constant in front of the
Yeah,
radiator
it depends on how you look at the signal.
Yeah.
Yes.
Alright.
Yes, please.
Is it possible to make the purple over to an orange? So it's just.
So you mean the purple is this one?
Yes.
Then
and the-
plus this and this one.
Yes.
Yes,
that's
you can
also
do that.
possible. Okay.
Again, you can look at the signal in different ways, but still, I mean, you follow the same approach. Okay, now we need to find the Fourier transform. As I said, you don't need to do the proofs. We just use the formula. Where was it? Here at the top there. So f of omega would be equal to, for the orange one, capital T is 4. So 4 times sinc of 4 omega divided by 2 plus 2. 2 is a constant, so I write it. Capital T is 2, so 2 times 2 of sinc 2 omega divided by 2, which we can simplify this one. So 4 sinc of 2 omega plus 4, 2 times 2 is 4, sinc of omega. And that would be the final answer for Fourier transformation. Okay. Any question for this example?
Can you explain again why is that?
You know, this is a rectangular, and I just showed you that the Fourier transformation of the rectangular is this formula. No matter what is omega, is it 0, not 0, this is the general formula we have. So I use this one. What is capital T? Capital T comes from, where is it? Capital T comes from here. The rest of small t divided by capital T. So I find that for the orange one, capital T is 4. So 4 times sinc of T is 4. 4 omega divided by 2. 4 omega divided by 2. Plus, I have a constant number 2. I write it as it is. So
Did you switch?
I just maybe it's easier for you to if I write it as a omega 4 divided by 2. It's the same.
Yes. Okay.
Or omega 2 divided by 2. Yeah. And then I did the same approach for the other one, and I just cancel out 1, 2 here, and also the other one here.
So if omega is 2 over 2, isn't it just sinc omega?
Yeah.
Yeah, that's why I wrote it at the end.
Okay,
Yeah.
that's why.
Yeah.
Okay.
Okay. So, any other question for this example? Okay. As you can see, for this rectangle, small t divided by t, it has to be always and always mirror with respect to y-axis. And the formula we obtained, and it is in the book, is in this case. Okay? A question which may come in mind, I think you have it in one of the exercises for today as well, is that how about if I have a rectangle like this? We don't see the mirroring. Height is 1. We don't see the mirroring with respect to y anymore. Why? Because the signal has some shifting. Actually, this is something which I will cover it next week. So I think in one of the exercise for today, in one of the plots, as far as I remembered, we have one example with shifting. Don't solve that because you have not learned it yet. Just skip that one small part and do the rest, okay? Because we talk about the Fourier transformation of rectangular with shifting next week. some number which is not 0, based on time scaling rule, as far as you have f of omega, you can use it here and use this formula. So 1 over absolute value of A multiplied by f of, instead of omega, replace or all omegas by omega divided by A. And use this one. You don't need to use the formula or anything, just directly use the formula which is here. I have an example here for you, which we can look at it together and see how this can be done. So from the first example today, I showed you that for signal we had the Fourier transformation was 1 over 1 plus I omega. So we obtained this together. And now I want to find the Fourier transformation of e to the power of minus at times u of at. So we have something, and now we have the time scaling factor of the signal. So you can see the difference is that all t's are now replaced with at. We can use the formula from previous slides. And if you do that, I should write it as, the Fourier would be 1 over absolute value of A, and then capital F of omega divided by A. Capital F in this case is the one you obtain it, 1 over 1 plus I, and now all omega should be replaced by omega divided by A. And that's it. So I have not used the definition or anything, just by following the rules. I think you can find this one in tables as well.
What is time scale? What is that used for?
Time scaling, it means that you can see you have a function f of t, and now you replace the t with at. So you multiply all t factors you have with a constant number such as a. Then it's called time scaling, because you scale the whatever value you had for t with a number. This is called time scaling. F of t becomes f of at.
Yeah, but what is the purpose?
For instance, if you want to make a signal double big as the original one,
Yeah.
then you just multiply whatever t values you have with 2,
Yeah.
then you scale it 2 times bigger.
Okay. So that's
Or if you want to make a signal half of the original one.
just to, if you want to like double it.
Or bigger, make the signal bigger or smaller.
Yeah.
This is how the scaling factor works.
But how do you do it reverse?
Smaller?
Yes.
Then, for instance, if you want to make it double, A should becomes 2, and if you want to make it half, A is half.
Okay.
Then you should play with the A number.
Yeah. Okay. You play with the A number.
Yeah, constant number. Any other question? That was all for today. I don't have any more lecture. But before going to the exercise, I want to do something else. But before that, do you have any questions? Okay. No question.
Hvad vil hun lave? Hvad vil hun lave? Tror du, hun tager en ny? Holder jeg ikke. Nå, nej, jeg så ikke. Jeg tager den ud. Jeg får det op og køre.
Okay. Actually, I want to use some time to do the midterm evaluation of this course. I want to know if there is anything I can improve, or if I do something good, which I should continue to doing that. I would like to have some feedbacks. So I give you 15 minutes time, and I leave the room during this 15 minutes so you can discuss among yourselves. please talk about